Today, we'll be covering how to build low-latency applications in Rust on ScyllaDB. As you may know, Rust is a low-level programming language with direct access to hardware and memory, and ScyllaDB, as we will see, is a NoSQL database designed to handle millions of operations per second. So we thought that since Rust and ScyllaDB are built for high performance, that they were a natural fit to build modern applications. So I'm Raouf, developer advocate here at ScyllaDB, and today I'm joined with Piotr Sarna, the architect and developer of the native Rust driver, and Felipe Cardinante Mendez, solution architect at ScyllaDB and the author of the sample app that we will be using today. So let's talk a little bit about our agenda. So the agenda is broken into three parts. After a quick background on ScyllaDB, Piotr will provide us with some background on the design and the architecture of the Rust driver. Next, Felipe will demonstrate three small programs that show how to connect to ScyllaDB cluster, load data, and run queries in Rust, with few tips and best practices thrown in. By the end of the workshop, you will have a good understanding of the Rust driver for ScyllaDB, how to install and work with ScyllaDB, and how to use the sample app. So let's get set up. Before we start the presentation, let me provide some instructions on how to obtain the sample application. So let me show you here on my screen. So I have the repo right here on GitHub. So you can find it on Phi-Mendez Rust driver example. And this is actually Felipe's GitHub repo. So I'm going to go ahead and clone the Git repository here using my terminal. Now let me clear this, and let me move to the directory and show you the folders here. So as you can see, we have three applications, and Felipe will tell you more about these applications. But we're also using Docker for this application. So if you don't have Docker, we'll provide you with a link to download it. Otherwise, I'm sure that most of you do. Okay, so in addition to that, please don't forget to join our user Slack channel and our Rust driver channel. And we'll be very happy to hear your feedback and suggestions to our approach to Rust. So before we get started, let's talk a little bit about ScyllaDB and Rust. Rust and ScyllaDB combine to help developers write safe, reliable applications that run at extremely low latency on high availability distributed systems. What makes ScyllaDB uniquely suited as a database for Rust applications is its shard per core architecture and asynchronous non-blocking runtime. And this is especially true for the types of low latency distributed applications that many developers are building, or in some cases are rebuilding in Rust. So this architecture lets ScyllaDB make full use of the power of modern hardware, giving it impressive scaling performance characteristics, capable of handling billions of operations per second with a P99 latency measured in single-digit milliseconds, with some of our users running clusters over 1,000 nodes. Today, we have a number of users who are actually rewriting critical streaming applications from Python over to Rust, just for the added performance and safety that it provides. If you're interested in learning more about the architecture, we have many tech talks and white papers on ScyllaDB's architecture that are all available on our website. And now I'd like to bring the guys back on. So why don't we start with Felipe?
Hey, Raouf. Hey, guys. How are you guys doing today?
Hey, doing pretty well. So thanks for joining us for this workshop, Felipe. So
welcome.
I have a couple of questions for you. So my first question is, in your own words, what is ScyllaDB and why should developers be interested?
So ScyllaDB is the next generation NoSQL database for developers and companies who care about high performance, high throughput, and low latencies. So as you have already explained, ScyllaDB has a unique architecture which makes very efficient use of modern hardware. And as you have also said, it also allows us to basically unlimitedly scale. ScyllaDB is capable of running workloads, very big workloads, over 1 million operations per second, and it can basically unlimitedly scale. As you have said, we have clusters with over 1,000 nodes.
Wow, that's pretty cool. And I have a follow-up question. So, what makes ScyllaDB unique?
Well, ScyllaDB is not just another NoSQL database. So as you can see around the market, there are many types of NoSQL databases. So ScyllaDB, we are constantly improving it to bring new technologies, new capabilities up to speed. So for example, ScyllaDB has its own CDC implementation. I know that Sarna in here is currently working to bring up to speed WebAssembly. We also have a feature that's called Workload Prioritization, which allows you to run analytics and real-time workloads under a single database without impacting your real-time workload latencies. We have exclusive features such as incremental compaction strategy that no other NoSQL database in the world has, and all of that is still maintaining very low tail latency. So in summary, what makes us unique? Well, if you care about performance and low latencies, you should be looking to Scylla.
Wow. Okay, yeah, sounds good. Thanks a lot, Felipe. So now, if you don't mind, let's bring Piotr for a few other questions.
Hi.
Hi, Piotr. So thanks for joining us today.
Sure.
So Piotr, you as the technical lead on the Rust driver project, can you tell us a little bit about why Rust Tokio and the async make it a great fit for building safe, reliable applications that are at extremely low latency on high availability distributed systems?
Sure. So modern applications need high concurrency in order to scale. And the asynchronous model has proven over the years to be a great fit for that purpose, especially with regard to strict latency requirements and general efficiency. And asynchronous Rust is based on a quite unique approach. Nothing's implicitly started in the background, and instead it's the programmer's responsibility to advance the state of asynchronous computations. And in order to do that, a runtime is customarily used. A runtime includes the capabilities of a scheduler, event loop, reactor. The names are different, but the idea is always similar in async frameworks. And due to asynchronous design, runtime is not part of the language, but instead there are multiple runtimes to choose from, or you can even implement your own. And we picked Tokio. Tokio is pretty much a standard choice due to its active development community, lots of features, in general ease of use. And side note, it would be perfect to not choose a single runtime, but to write our driver in a runtime agnostic way. But we decided that the ecosystem is not yet ready for it. There are tons of important bits in Tokio, like good TCP utils, timers, and other things that are not easy to code in a fully generic way. But back to our driver, it allows high concurrency and scalability by using this async mechanism provided by Tokio, for instance, channels, buffered readers, writers, and so on. And it's also shard aware, which means that by default, it will establish a connection per each CPU core of each database node. And thanks to per core connections, we're able to squeeze much more performance out of the processors, their caches, and generally from the hardware.
Sounds good. Yeah, no, thank you very much, Sarna. So with that, I have actually a quick poll question for you. So before we get started, can you tell us how proficient you are in the Rust language? So is it your primary language? Are you building production application, but it's not your main language? Or are you're using advanced features, but it's not in production? You're learning, like certain people I know, or it's on your list of the things that you need to learn. All right. So, and with that, let's bring our technology specialist and the author of the sample app that we're going to use today, Felipe. Let's hand it to you.
Thank you very much for your kind words, Rauf. And from the previous poll that you have just said, trust to be told, I have seen my name was in there. I am still a novice Rust developer, so I am likely the less capable in class. Sorry about that. But before we actually get started to actually seeing some code, we have a fairly interesting question already from the audience, and I think that question was just popped up, which is, as you are experienced with other languages, what did you think of this as your first Rust project? Well, thank you very much for the question. As a novice Rust developer, I can tell you that I have run into some hiccups while trying to port my code into Rust, but not because the language is hard to learn or anything, but because Rust forces us to write safe code so that we wouldn't shoot ourselves in the foot in the future. This is a very noticeable characteristic of the language that if you are a starter just like me, I'm sure that you are going to enjoy it quite a lot. And before we actually start explaining about the code, I have one question for you, Sarna. So what are the benefits of using our Rust driver implementation rather than the CDRS driver, which is also Rust native, and that can be found online?
Yeah, so we also investigated CDRS first, but first of all, it's not asynchronous, so at some point you can't just use it with high enough concurrency. It also had a number of bugs, some with prepared statements, which are crucial for Scylla's performance, and the general performance is also substantially lower than ours, according to our benchmarks.
Very interesting. Thank you. Thank you very much, Sarna. All right, so let's go back to the slides. And before we actually take a look into the actual Rust code that we are going to be discussing today, let me provide a bit of context over what we are going to do and see next. We are going to demonstrate 3 different and small Rust programs, which will cover best practices around how to connect and fully utilize your ScyllaDB cluster. Our sample application, or our sample code, is a simple application that simulates 100 IoT devices recording temperature samples against the database every 300 seconds, or 5 minutes for that matter. And we record those samples for a period of 3 days. It demonstrates an append-only time series type of use case. The first program that we are going to see is called the metric collector. This program, simply put, will create the necessary resources, key space, and tables on the database and generate and write data to it. The second program is called the metric reader, and it demonstrates how to efficiently perform full table scans against ScyllaDB. In that program, we will split the token ring into smaller chunks, and using the token function along with the bypass cache SQL extension, we will count how many temperature records each device has. This program is a good example on how to efficiently perform analytics type of queries using the Rust driver, and simply put, it tries to apply similar principles as technologies such as Apache Spark or Presto, employ when running ad hoc types of queries against the database. All right. The third and last program that we are going to see is more of a simplistic one, but can be seen as a real-time example for reading data. In that program, as opposed to the previous one, which is basically an analytics one, we know which IoT device we want to query from. By using range queries, and we are basically going to use the max, average, and minimum SQL functions in order to retrieve statistics for a specific single device comprising a given period of time. All right? So one last heads up before we get started. As it was pointed out in our initial poll, I'm still a beginner Rust developer, and these specific programs were initially written for me to learn the Rust language. And truth be told, I'm still doing my I'm still in my first steps towards learning Rust, and I would love to hear your feedback. Should I have missed some Rust language specific best practices? Therefore, for the actual demonstration part, we will cover the ScyllaDB Rust driver specifics more rather than the Rust language specifics. So, Sarna, a quick question for you that we typically get quite a lot. Does the Rust driver that we have works with Cassandra?
Yeah, it does. One of our goals was to be fully compatible. The driver is optimized for ScyllaDB. We have a couple of tricks that make the driver way faster with ScyllaDB, but it's also still the fastest Rust driver for Cassandra as well, according to the benchmarks that we made.
You hear that, the audience? The fastest driver for ScyllaDB. Thank you very much, Sarna. All right, so now let's take a look into our code. So to save us some time, I'll have already brought up our working environment, which basically contains 3 Scylla nodes, which is our cluster, and our Rust application container. Okay, so what you have to do after you fire up the Docker Compose, basically you're going to start your environment like this, and you can see that my environment is already set up. Then you can run Docker PS, and then you will be able to see that you have the ScyllaDB1, ScyllaDB2, ScyllaDB3 containers, which comprise our cluster, and then we have the Rust application container. Okay, so to make your life easier, after you run the command to start your containers, I'm going to ask you to run docker compose logs -f in case you haven't, and then you are going to see on the logs. Actually, I think I lost the logs, you are going to see a message. Let me just filter by the Rust application that we have. You are going to, oops, wrong name. You are basically going to see this message over here that ScyllaDB is up and available. And when you see that message, you are ready to move forward. Okay? So there's one additional thing that you want you to do. Open a new terminal, and let's connect to one of our Scylla containers via CQL S8. The command for us to do that is basically Scylla docker exec -it ScyllaDB. I'm going to choose the container 1 and then CQL S8. Okay? And what I want you to do is to run the command describe schema. Okay? And this command will basically output nothing to the screen, which makes sense since we basically have nothing. We haven't run anything yet. Okay, so keep the shell open and let's move to another tab, which I called here the Rust tab. And what we are going to do over here is to basically log in within our get a session to our Rust application container. Okay, and then we are in the Rust application container. So one last question that just occurred me around our Rust driver implementation, Sarna, and I promise it will be the last one.
Right.
I recall that another implementation that we often see people using are the Cassandra CPP driver with Rust bindings. Can you elaborate a bit on that and tell me which one is the best performant?
Well, our benchmark showed that we're still the fastest, although Cassandra CPP is indeed quite close. But still, it's based on bindings to the C++ driver. So first of all, it's less safe than native Rust. But in terms of performance, it still involves two event loops: one from Tokio from Rust, and another from the C++ code from libuv. So it uses more CPU and has slightly higher latencies. So all in all, we're better, but it's indeed the close second.
Thank you. And is there any plan to make it the other way around? Rust driver that we will eventually replace the CPP driver?
Indeed, it's work in progress. We're preparing a second reverse binding to make a C++ driver that simply binds to our Rust implementation. Although C++'s API is quite large, so it will take a while. But once it's done, it should be really great.
Thank you very much, man. All right, so let's get back to our quick demo. So from here, let's run our first Rust program, which is the metric key collector. And as we saw, the metric key collector is basically going to create our database resources and feed the initial data to the database. So in order to do that, I'm going to run cargo run --bin metric collector, and I'm going to pass the IP of one of the contact nodes of our cluster. Okay, in this case, I'm using 172.19.02. And I'm going to press enter, and that's basically it. Okay, that quick, we have run 86,402 queries against ScyllaDB and wrote our data. At the end of every program, the driver metrics are going to be printed on the screen, okay, which you can use to gain some insights of its overall performance. Another word of caution. Do note that our entire infrastructure here is being run on a consumer-grade laptop and in Docker, which, in my view, it only makes those results even more impressive. Okay, so remember that shell session which we had opened before to connect to SQL S8? Well, let's go back to it and let's run the describe schema command again. And then we can see over here that the resources were created after we have run the first program. Okay, do we have any data on it? Well, let's see. Let's run a select star from the table that was created with a limited one. And yes, we have data. Okay, so now that we are past the first program, let's examine its code. So I'm going to run our old beloved VI and open the main function. So before we actually deep dive into the actual Rust driver specifics, I want to briefly speak about the parallel constant that you are seeing over here. For this specific example, since we are ingesting a lot of data at once, we are also defining a max concurrency of 2048 in-flight queries at a given moment. In general, when you are designing your application, it's commonly a good practice to ensure that you have a mechanism to control the concurrency in order to avoid overwhelming the database. Should this not be possible, ScyllaDB has a configuration option that's capable of shedding requests, or if you feel like you are hitting a hard limit, you can also scale out your cluster and or review your access patterns / data modeling. Okay, so the first thing that our program does is to basically parse the command line arguments to determine our cluster contact points and the data center name we want to target. And as you can see, the default is to contact on localhost and data center 1 for the data center name. But you can change it to whatever you want when you are going to execute that program. So once the driver connects to the cluster, remember that we have a 3-node cluster. What the Rust driver is going to do, it will automatically discover the whole cluster topology, and it will automatically open connection to other nodes that are part of the cluster automatically. The typical recommendation is for you to have at least one node from a different rack in the data center as contact points for your application. For example, in a minimal production workload, you will typically have a deployment of a 3-node cluster where each node is located in a different availability zone. And therefore, it makes sense for us to specify all 3 nodes as our contact points, since the failure of a single node won't prevent new application clients from connecting. Okay, so the next step that we do is basically to define the key space and table that we are going to write our data to. We chose IoT and devices as its names respectively. Okay, what we do next is basically to initiate a cluster session, and one thing that you will want to typically specify is the load balancing policy that you are going to use for your queries. So the load balancing policy basically tells the driver which nodes it should use, it should contact for when you are executing your queries. We are using the GC-aware round-robin policy, which means that the driver will ensure your queries are only being sent to nodes located in the same data center that we specified earlier. Okay, this is helpful when you have a multi-GC or multi-region solution and you want to avoid your application from sending queries to a different location. In fact, as a general good practice, you will typically want to collocate your application close to the database for latency reasons. And this basically brings me to another question for you, Sarna. Is it possible to tell the driver to connect to nodes only from a specific data center in a multi-region setup using the Rust driver?
Well, if you specify your own load balancing policy, which you can do, then you can decide whatever you want. The actual implementation would be yours. So it would be up to you as a programmer to decide which nodes you return. And if you decide only to return a single data center, then yeah, why not? By the way, we are in the middle of rewriting this layer of load balancing policies, but it still works well right now. And I already know that some community members already implemented their own load balancing policies, mostly for testing purposes, for using one node and not the other. But in particular, using one DC would be a good candidate for that.
Yeah, thank you very much for this. And from your experience, how easy it is to create a custom load balancing policy?
It's from my experience, it's super trivial because I also implemented the other ones, not directly, but reviewed it and all. But it boils down to copy pasting an existing one and then adding your stuff on top of it. So it's quite easy. It's it's kind of a Stack Overflow experience. You just copy paste stuff and change it a little bit, so it works for you.
All right, thank you very much, man, for this feedback. All right, so let's continue. So what we do after we specify the DC-aware round-robin policy is basically we add the token-aware round-robin policy to the DC-aware on top of the DC-aware round policy to ensure that our queries are being sent to nodes that are actual replicas of the data that we are writing to or reading from. For example, you may have a 6-node cluster and a replication factor of 3, which means that only 3 copies of your data will reside across different nodes of your cluster. Make sense? With token awareness, reads and writes to your data will go directly to the nodes which are also replicas. Therefore, this is an additional tuning that we typically do to avoid network round trips and further reduce on latency. Okay, and as we have just spoke, there are other loading balancing policies available within the driver, and since one solution never fits all, you can even create a policy of your own, as Sarna has already explained it. All right, so we then initiate the connection. Okay. We basically specify that we want compression. We are using the LZ4 algorithm, but we also support Snappy, and we specify the credentials, user and password that you can see over here in order to connect to the cluster. All right. So after we connect, the next thing that we do is, simply put, since we know that our cluster is empty, or it may not be empty, we start creating the key space and table resources that we are going to need in order to ingest our data. And you can see that we use the if not exists so that those statements don't fail if we try to execute them again. What we do right after sending the commands to create a key space and creating a table is to check for schema agreement. So one of the things that I want you to keep in mind when you are doing schema changes in a distributed database like ScyllaDB is to ensure that you always check whether your schema gets in agreement before you proceed on doing other changes. So the Rust driver provides us a method which you can use in order to ensure whether your cluster got in agreement before proceeding. And then we do this check. If we got into agreement, good, we are going to proceed. Otherwise, something wrong happened and we simply quit the program execution. Okay? So after we are past the key space and table creation steps, our next step is to prepare our insert statement, which we can see over here. We are using prepared statements. So, Sarna, I've read somewhere that only prepared statements use the token-aware routing. Why is that? And how complex would it be for the driver to automatically infer the correct partition to route queries to its respective replicas if I did not use it, prepared statements?
Right. So first of all, if you, I assume that if you want to use token awareness, you care about performance, and in that case, you should never issue non-prepared statements in the first place. Well, the reason is that when you prepare a statement, Scylla or Cassandra would return prepared metadata from your query, which would include some information how to easily locate the partition key from which you can compute the token. For non-prepared statements, if we wanted to do that from the driver side, we would need to parse the CQL statement, so repeat the job that ScyllaDB already does. And then figure out which one, which columns are from the partition key, and then compute the token from that. And that makes no sense because it's a lot of work, and you're issuing a non-prepared statement, so it's clear you don't really care about the performance. The prepared statements are really, really important, and that's why we implemented token awareness just for these statements. That's also what most, if not all, other drivers also do, because there's no point in parsing SQL client side.
Thank you very much, man. This is very enlightening. So, guys, please use prepared statements whenever you can. All right, let's continue then. Thank you very much, Sarna. So, what we do next after we prepared our statement, basically, we are going to set our query's consistency. And we are specifying that we want a consistency of local quorum, which means that the majority of replicas must acknowledge the operation before we consider it successful. So remember, we have a 3-node cluster and we are using a replication factor of 3. Local quorum basically means that at least 2 nodes must reply back to our operations before it's considered successful. Okay. Finally, we set a retry policy over here, which tells the driver to retry queries that could have failed if it believes that there is a high chance of them completing. This line is here for educational purposes only, as this is the default. Similarly, as the low-latency policy that we just discussed, there is another retry policy that you can use, which is called default true retry policy, which effectively never retries. Or you can even create a retry policy of your own. For example, you may have an analytics type of use case where you don't want to queries, where you basically don't care if the queries have failed or not. Whereas you also may have, in addition to that analytics use case, a real-time use case that you always want those queries to succeed, and therefore you want a retry policy. So this is an example situation where you may want to specify a different retry policy other than the default. All right. So what we do next? So we have done a lot of things. We created tables, we prepared statements, connected to the cluster, set the consistency, set the retry policy. What we do after doing all of that? Well, we start ingesting our data finally. So we basically start a loop fashion, okay, where basically we loop through the number of devices that exist, and we create a number of semaphores before doing so that you can see over here. And here is why I started speaking about the parallelism, because this is the number of semaphores that we are basically going to create. And then we do a Tokio task that's basically going to call the execute method that you can see over here, and to write to our database. Okay, that's simple. And once we finish writing to the database, we wait for our in-flight requests to finish, and we print out to the screen the driver metrics that we have seen when we have run the initial example. Okay, so this is a very nice driver feature that you want to integrate on along with your monitoring metrics, as it will allow you to quickly have live insights of not only how ScyllaDB is performing, but also how your application is performing when communicating with ScyllaDB. And Sarna, a question for you: is there is there any other kind of metrics that you are looking for to bring up to speed with the Rust driver for now?
I'm not aware of any particular metrics, but we are looking into integrating OpenTelemetry in general. So that would bring lots more observability once it's done. So you can open some project like Zipkin and browse what happens and when. So that will be a whole another layer, and hopefully we'll have something by the end of this year, maybe.
Nice. Open telemetry is really nice. Well, so upcoming features. Thanks, man. All right. So now that you have seen the basics of our program, how to properly connect to ScyllaDB and execute statements against it, let's move back to our Rust application container and run our second program. Similarly, as we have run the first one, I'm simply going to change the name of the program here, and I'm going to call the metric reader. Remember, the first program wrote data to the database. The second one is basically going to do what we call a full table scan. So our second program is very similar to the first one, but instead of writing data, it will efficiently perform a full table scan and count how many metrics per device have been collected. Okay? To efficiently perform a full table scan, we needed to remember the way that data is distributed across ScyllaDB cluster. First, when we are modeling our data, during the table creation, we needed to specify what's going to be our partition key. The partition key is then hashed using the murmur tree algorithm, and in return, we get a token responsible, we get a token. And that token will determine to which node is responsible for that information, okay? Depending on our key space replication factor, additional nodes will also hold the data for that given partition as replicas, which is how ScyllaDB achieves high availability. Therefore, the data from our first program was, simply put, spread across what we call our clustered token ring. All right? So let's take a look into the code for our second program, which is the metric reader. And what this second program does, let's skip the part where we basically parse the statements, we create the connection, etc. This is the interesting part. So what the second program does is to basically split our token ring to smaller chunks, okay? So what we do, we define the parallelism of this program or its concurrency as the number of nodes that we have in the cluster, which you can see over here, times the number of CPUs that exist. And we also add a factor of 3 in order to ensure that we have enough concurrency in order to keep all of our CPUs busy, okay? So with that parallelism in mind, what we do, we basically are going to multiply this value to 1,000, which is simply put how many queries we are going to send in total. All right, then we get how many tokens exist, and then we divide by our total token ring to the number of sub-ranges. This is the name that I have called it, this variable, in order to get what I call the chunk size. And the chunk size is basically going to determine the number of iterations or the number of queries that we needed to run in order to fully scan our token ring. Okay? Make sense? So what we do next, basically, we are basically going to prepare our statement. We have already spoken in the first program how important it is for you to run prepared statements. But now what we are doing over here is to use the token functions, and we are going to pass the values that we have generated before. Okay. In addition to that, we are also specifying the bypass cache CQL function. And what is this function? So The bypass cache operand is something that you will typically always want to have when running such types of full table scans. What it does, simply put, is to tell the database not to populate its cache with the data that it reads. Therefore, our reads are going to disk. Of course, this has a latency penalty, but generally speaking, when you have analytics and real-time use case running on top of ScyllaDB altogether, you won't want your analytics to pollute your cache, as this may cause increased latencies over our real-time workload. Okay? So what our program does next, we set up the retry policy, and then we move forward in a loop fashion. We create again the number of semaphores defined by our parallelism, and then we iterate through our token ring in parallel to fetch as much information as we can as fast as possible, which you can see over here. So for the from the minimum token to the max token, we basically do steps by the chunk size that we have generated before, and then we run queries over it. Then once again, we wait for the in-flight queries to finish, and we print the same metrics at the end. Okay, and this is the explanation of the second program. Okay, so let's move back to our Rust application container and execute our third and final program, which is the Uuid Finder. So this one is a little bit more complicated because we need to specify one of the UUIDs that have been generated. And I have one over here. And if you take a look into our GitHub repo, you are also going to be able to see that there are some UUIDs that you can use in order to test the functionality of this program. And then what am I going to send next is the period of time that I want my queries to be running. So from January 1st, midnight to until 11 p.m. Okay, and what's missing over here is that I need to pass the contact point of my cluster. Okay, so this one is simple. It's complicated to be executed, but simple to understand. Simply put, in this one, as opposed to the previous one, we now know what is the partition that we want to query, which is the UUID that we specified over here and that you can see on those 3 lines. Since we know the partition that we want to query, we are basically doing what we call a range query, and we will basically be using the max, minimum, and average functions that in order to retrieve the data that for the time period that we requested for. Okay, one thing that I want you to keep in mind is that the temperature values, they are generated more or less randomly. So don't worry if you get some weird results, as we are seeing over here. The max was 49 and the minimal was minus 39. So yeah, this is a very discrepant result. But let's take a look into the code fairly quickly so we can see how we basically created this program. As you can see, we have some UUID hard-coded over here in case you do not want to specify any time frame. And what we do right after, this is very important in case you are going to work with dates using the Rust driver, is that I struggled a little bit in order to get this working. You have to convert your dates to a duration, okay? And this is basically how I converted the user input eventually to a duration in order to issue my queries in order to do range queries across the timestamps. So After we get past parsing the user input, we again initiate a cluster session, and then we prepare the statements whether we are using the max, minimum, and average functions. And here, what we are doing is we are basically using what we call range query, which is very efficient because we are querying a single partition. Okay, so what we do next? We basically bind the parameters and execute the given statements, the prepared statements that we have prepared, that you can see over here. So here we are executing the max, and here we are executing the minimal, and here we are executing the average. And then we print back to the screen the results that you can see over here. And finally, we print the metrics again. Okay? So this brings us to the end of our coding session. I hope you have enjoyed. And again, should you have any feedback or suggestion, please feel free to reach me out. And that's it. Thanks, guys. Let me bring back Rauf. So, Rauf, back to you.
All right. Well, thanks a lot, Felipe. I have to say that looking at that data, those temperatures, I come from a place where those numbers are totally realistic. But can you tell us, guys, if that that code worked for you and what's your experience with it? From what I see, Felipe is a total master in Rust. What I want to show you now is actually how to connect to Scylla Cloud. So Felipe showed us how you can run ScyllaDB on your local machine using Docker. You can do that if you want to run it in your local machine. But you also have the option of using Scylla Cloud. And let me show you here in my monitor so you can see on the browser here. You can find Scylla Cloud on our website, so scylladb.com/cloud. And we have two new free trials. So we have a free trial for builders, which is valid for 30 days. But we also have a production evaluation that you can use for benchmarking, that you can run for up to 48 hours. But please feel free to reach out to us in order, and we'll be happy to help you to get the most out of your free trial. So highly encouraged to go and check it out, create an account. But this is how it looks like. So I have an account, and this is the dashboard. So here I see all the clusters that I have up and running, and let me walk you through how to create a cluster. So you can create a cluster in one of your favorite cloud providers. So here you have AWS and Google Cloud. You can name a cluster. You can define the IP addresses that you want to add. You can also use VPC peering to secure your network. Select the location of the cluster, the type of machine, and replication factor. Felipe spoke about replication factor and the number of nodes, and then launch, and then create a cluster. But I'm not going to do that because I have one that is already ready for me. But once you do that, this is what you're going to have. So you're going to have the IP addresses of your nodes. You're going to have your data center. And if you click on this connect tab here, you'll have different instructions on how to connect to ScyllaDB. So you can do it through SQL/SH, or you can do it using your favorite languages. But today we spoke about Rust. So let's actually get back to the Rust code that Felipe showed you earlier. Here, what we have for you here by default, if you're using ScyllaDB locally on Docker, is you have a host, you have a data center, you have a username and a password. So all you need to do to run the same code but using ScyllaDB is to change these. Basically, you change the username, the password, the host, and the data center. And if I get back, I have all these informations provided for me. So I have the data center. I have so the nodes. It could be one of the nodes IPs. And if I go to the connect in instructions, then I have username and I also have my password. So the way we did that also through the code is, if you notice that you can pass some arguments here, and you can pass host, DC, username, and password as arguments. And those are going to be used in the session to create the session to connect to the database. So let me do that. So here, when I'm going to use the same code that a command that Felipe used before. So cargo run bin. I'm gonna run the metric collector application, and I added my host. I added my DC and my username and password. Here you see my password, but I highly encourage you to use your own cluster, because I'm going to delete this cluster right after this presentation. So let me actually run this. So it's connecting to the host, and then it's going to execute the program. And then I'm going to have the metrics right here displayed. So you can notice something. You can notice that, for example, the average latency and the 99 latency percentile is way higher than what Felipe showed before. And it's not because the database is less performant in the cloud, but it's simply because the metrics are client side metrics. So the driver's metrics are client side metrics, and they're running on the client. And in order for you to test your performance and know how well your latency was, we have actually the monitoring dashboard for you that you can click right here. I opened it before, and it's the monitoring dashboard is based on Grafana and Prometheus, and I highly encourage you to read about it on our website if you're more interested. But here I can see that my average like I can see here I have a bump. This is this is the one that just happened here. So according to the time looks accurate, and I can see that my average write was under 1 millisecond. And I can see my 99th percentile as well was about the same. So this is regarding the Scylla Cloud. One other test that I want to do is actually, I did it beforehand, but I showed you how to connect using SQL-SH, but let me get back to it actually and show it to you again. So you can connect to your cluster running this this command here. So Docker run, you specify the entry point, the username and password again, and also the host. And you can connect using SQL-SH, and here I can do describe schema. And I see that, and I see also that my schema was is here for me, so everything worked according to plan. All right, so let me get back to the slides, and I think we have a poll for you. All right, so can you tell us a little bit more about the database that you use? So do you use Postgres, MySQL, DynamoDB, MongoDB, Apache Cassandra, ScyllaDB, CockroachDB, Yugabyte, Redis, other? Please let us know what database you're using to build on your REST application. And with that, I would like to invite the guys back, and we're open for Q&A. So let's welcome your questions. Hey guys,
Hey.
welcome back.
Hi.
Well, thanks for for the presentation, for the code, and answering all the questions. But we still have a few questions for you. So we received this question just now. So What's next for Rust at ScyllaDB? And I don't know who can take this one.
I will, I guess. Right. What's next? Aside from the driver, we're also planning on coding some Rust in Scilla core as well. We're starting with rewriting our user-defined functions layer from C++ to Rust in order to have better support for WebAssembly. So that's a start, and who knows what's next. Once we have all the environment set up, we can decide that some other independent modules can get rewritten to be safer.
And sorry, a follow-up question around that. Today we have the CDC driver for Java and Go. Are you looking towards bringing CDC up to speed within the Rust driver as well?
Yeah, it's an ongoing project. It's actually a student project. The guys are supposed to be finishing that around June if they want to, graduate. So hopefully they will finish by then, and we'll have something to be published.
Thank you. Very nice.
All right. So I have another question for you guys. Could you please elaborate more on what shard awareness is?
Yes, let me take that one, Sarn, and then you can chime in. So, shard awareness is basically an extension that we have implemented on top of the SQL protocol. So, as you have spoken during the beginning of the presentation, in Scilla architecture, we shard our data per CPU, which we call shards. Whereas in Cassandra, your data is sharded by node. So, what we did, since we have this differentiation, we basically added a SQL extension to the protocol. And whenever, this is how it works in general. Whenever the driver is going to connect to a server, it's going to send a command, which is called the options command. And the server is going to reply back to the driver which features it supports, which version you are connecting to, if you are connecting to a Cassandra server 2, 3, or 4, or if you are connecting to Scilla. And what we added was what we call the shard awareness extension, which basically is going to tell the driver that the server that you are connecting to supports this extension. And once the Scilla driver gets this information, what it will do is to open additional connections to each node of your cluster, and each connection will point to a specific shard or one specific CPU of your cluster. And the result is that you are going to have much better latencies, because now your queries are going to be routed directly to the CPU that's responsible for the information, and no longer only to the node. And therefore, we are going to avoid the cross CPU hops that may happen while you are running your queries.
Thanks for that, Felipe. And we have another Rust-related question. So I don't know who wants to take this one, but can we have unit tests with Tokio? For instance, async unit tests.
We do already. Well, our driver is inherently 100% async, so our tests are async as well. Tokio actually already has the whole test harness for unit tests, so you can literally just mark your test with Tokio :test, and then write an async chunk of code and then run it. That's what we already do. You can just browse the source code of our driver and find quite a few hundred tests that are async in Tokio.
Okay, and I have one final question. So we spoke about CDC, and one question is, what is CDC?
So, very good question. So, CDC stands for Change Data Capture, which is basically a mechanism that you use in order to be able to replay mutations from the queries that you sent against the database. So, our CDC implementation supports what we call the pre-image, the mutations themselves, the deltas, and the post-image. which means that every time you write to the database, you delete or update, an entry is going to be added to the CDC log, and then you can feed that information, I don't know, to Kafka, and from Kafka you can feed it to Elasticsearch, which would allow you to run other types of workloads. You can do pretty much whatever you want. And one very natural use case for CDC would be within the fraud detection industry. So where basically all the inserts and updates that you do are going to be fed to a downstream system, which is then going to be responsible to doing analysis of the mutations that are coming in, so that you can ensure your company's capital and your users' security. Okay.
All right. Well, thanks a lot, guys, for today. Thanks a lot for answering the questions. So I see that we have a few more questions, but maybe we're running a little bit out of time. We'd be very happy to answer more in the next Rust workshops. So if you're interested in ScyllaDB and what we're doing with Rust, we have other videos for you to watch and other presentations for you to watch. So please feel free to go to our website, ScyllaDB.com/webinar, and you'll find all this great content for you there. And with that, thank you very much, and we'll see you next time.